5, and your M star, your effective mass of electron, is this expression. So 1.1, yeah, you know that this 9 times 10 to the power 0.11 times 10 to the power of 31 is the mass of electron, isn't it? So you have to times it with this factor so that you are taking into consideration that your electron is in a crystal. And of course, you can just calculate it. Because E plus KT, yeah. So your E cancel, EC you cancel, so you are left with KT. So your KT, K is the Boltzmann constant, and your T is your temperature, 300 degrees. And voila, what you get is, so you can see that your density of state is very high. It's 10 to the power of 19. This is very large, a very large number. Okay, not to worry, because this value of NC are going to be given during exam, yeah? So it's a constant. So I'm going to give it to you, so not to worry about it. Okay, but this one is an exercise for you on how to calculate it. Right, we have talked about the energy, the density of states of energy, how to get it. So it's either your NC or your NV. But now, what about the probability of occupancy? Yeah, how are you going to find it? So, and probability of occupancy is the number of electrons divided by the quantum energy state. So, how are you going to calculate this one? Yeah, the probability of it. The issue is, yeah, there are many electrons. So the electron characteristic of it, so we cannot use each and individual electron as before. So we have to use something statistical because there's a lot of electrons. So what we are going to use are the average of all electrons. Yeah? So we have to use the statistical formulations in terms of the probability. So, actually there are 3 main statistical values, formulations that we are going to use. But as Maxwell-Boltzmann, Bose-Einstein, and the Maxwell-Boltzmann, Maxwell-Boltzmann, Bose-Einstein, and Fermi-Dirac. If you look here, Maxwell-Boltzmann say particles are distinguishable. Bose-Einstein say the condition of it is particles are indistinguishable, and Fermi-Dirac also say that particle is indistinguishable. But the thing is, for electrons, we cannot differentiate between one electron with another electron because electron A and electron B is still electron, isn't it? So, we cannot use Maxwell-Boltzmann then because particles are indistinguishable. Our electrons are indistinguishable. So, we have to strike out our Maxwell-Boltzmann statistics formulation for our probability. Next, we have to look at Bose-Einstein and Fermi-Dirac. Which one are we going to choose? Yeah, which formulation for our probability? So, if we look at here, Bose-Einstein say there is no limit to the number of particles occupying a quantum energy state. And Fermi-Dirac say only one particle occupying a quantum energy state. If you can recall, from the Pauli exclusive principle, I mean, you have learned it in atomic physics, only one electron occupying a quantum energy state. So that means we have to track out the Einstein, isn't it? The statistics, because it says no limit. Whereas we know from Pauli exclusive principle, it says that only one particle occupying a quantum energy state. So that means Bose-Einstein is also out. So what we are left with is only the Fermi direct statistics. Okay. So that's how we come up with for our function of f of t being 1 over 1 plus e exponential e minus e Fermi divided by kT. Because all this is the Fermi direct probability. Okay? As for the whole, of course, we know probability 1 or 0, between 1 and 0. So, electron hole, it must be 1 minus the probability of finding an electron. So, is there any questions so far? Okay, so there's no question, so we can move on. So let's find what is the Fermi direct probability of finding an electron at E Fermi. Yeah, at E Fermi. So let's say we replace this E with E Fermi. So what are we going to get? So we just substitute our E with our E Fermi. Our Fermi direct statistics. So we would like to know what is the probability of finding electron at E Fermi. So we put our E Fermi here. So e to the power of 0 divided by kT. So e to the power of 0. E to the power of 0 is 1. E to the power of 0. Yeah, e to the power of 0 is 1. So we get that the probability of finding an electron at Fermi level is equals to half. For getting at E Fermi. So at E Fermi, the probability of getting it is half, 0.5. Or if we draw it, the probability of finding it at E Fermi, we draw it, we can get it, probability of half. But the thing is, if we look at this whole equation, it's kind of complicated, isn't it? Complicated. Yeah, because of this expression. So, how can we simplify it? So, it's possible for us to simplify it a bit later. We are going to simplify it, but before that, let's see. Okay, never mind. We just skip this one first. We go how to simplify it. So Yeah, it's kind of complicated, but how are you going to simplify it? So for cases, our E level, our E level is minus our F, our B Fermi, is if it is much greater than KT, which is about yeah, KT at 300 K, our QT is about 0.0259 eV, or your E minus EF is much greater than QT, then it's possible for us to simplify this, complicated looking expression. Our complicated looking expression into something that it's more manageable. So it equals to this expression. Which is there. Where this one is called Boltzmann approximation of the Fermi direct probability. Because most of our cases, our E level is the difference between our E and also our E Fermi is much greater than 3 kT. So most of the time we are going to use this expression to represent our Fermi direct probability function. So we don't have to use this complicated equation. So we are going to use the one that's been simplified. Okay, let's see how this equation, how are we going to use this equation, the simplified version, because we have seen just now, using the complicated function in order to calculate the probability of finding the electron at Fermi. What about for the other energy level? So let's say, calculate the probability of energy state at the edge of the conduction band at 300 K being occupied by an electron if the Fermi level is 0.25 eV below the conduction band edge. So you see here that your key. So your key is at this particular number, isn't it? So your Fermi level is the difference between the Fermi level and the conduction band edge. So since 0.25 is much more than 3 kT, so we are able to use the Boltzmann approximation in order to calculate the probability of an energy state. Okay, we just plug in the equation. So where we know that our EC plus our minus EF is equals to 0.25. And our Kp, of course, is, like I said just now, is 0.0259. So, get that number. If you look here again, isn't it? This number is very small, 10 to the power of -5. So the probability of finding an electron at 300 K at that particular level is very small. So if let's say, look at this one again. So let's say our E is F Fermi is below the conduction band. Let's say our conduction band is somewhere here. So it's EC here. So the probability, yeah, is here, around here, very, very small. Okay. So when we know that this one is about 0.35 eV, and the probability is very, very small. You can have it, okay. Because at 300K, it's very, very small. So this is equal to 0.5. How many times? Negative 5. So the factor of negative 5, negative 4 smaller of a magnitude 0.4 smaller. So the probability of finding it, yeah, at the conduction band edge is very, very small. Okay. Is there any question? Before we go and calculate for the whole this one, let's just go shortly see the effect of temperature on the probability function just now. Okay. Just now we look at how to simplify the probability of finding an electron. Like just now, yeah, at 300 degrees K, which is about room temperature. The probability of finding the electron at the edge of the conduction band is very small. But okay, so let's look at 0K. So let's say this is our conduction at the edge of the conduction band, and this one is the edge of the valence band, and let's have this line that acts as the E Fermi. So at 0K, so we know that this is our equation just now. Let's use the difficult one and the complicated one, yeah, because we are not going to have that approximation case. So just use the general case. If at 0K, you can see that more than E Fermi at the E band edge, the probability of finding the electron there is 0. Okay? And below the conduction band edge, below the E Fermi, the probability of finding an electron is 1. 0K. So how are you going to get it as 0? Here. So if you look here, yeah, our EF so our E, if E more than EF, yeah, our E, let's say our E is here, yeah, if E more than EF, so what the difference between these two? So the difference between these both, this expression, yeah, is equals to be positive. Positive divide by, something positive divide by 0. So you are going to get this whole thing as infinity, isn't it? So E to the power of infinity is infinity, isn't it? E to the power of infinity is approximately infinity. So this whole expression is going to be infinity, 1 over infinity. So our F is equals to 0. So this expression is positive over 0, so we get e to the power of infinity. So e to the power of infinity is infinity, so 1 over infinity is 0. So we get this one as 0. But what about this as 1, yeah? 0 then EF. Okay, so if E minus EF or somewhere here, so you are going to get the difference between these two is something negative. Negative over 0. So we have is equals to negative infinity. So E to the power of negative infinity is 0. So 1 over 0. So it's equals to 1 over 0. E to the power of E is 0. So E is equals to 1 over 1 plus 0. So E to the power of negative infinity is 0. So 1 plus 1 plus 0. So we get, that one is 1. For E less than E F. So that's why we have our probability of finding it as 1. Okay. So that's basically about how effect of temperature. Then you can look at for 300K and also for 400K, where you can see that there's higher probability of electron being occupied at this particular energy state. Okay. At energy state here, so lower temperature, at higher temperature, there is a high probability of it. And also, you can see if at this particular junction, yeah, less probability of being occupied by an electron and more probability of being occupied by an electron. You can see that the effect of temperature. That's about the temperature dependence. Let's have it all. Yeah. So now we can have it all together. So for electrons, so that's the equation where you can see in your textbook. So this is the effective density of state, and this is the Fermi level location. So in order to use it, okay, calculate the silicon electron concentration at 300K if the Fermi level is 0.25 eV below the conduction band edge. So you just use, so this one the effective density of state, and this one is the Boltzmann approximation of your probability function just now. So you just put all the value in it. So you get, so large energy density that we said just now, and the probability being small, so you get something to the power of 10 to the 15. So it's just plain easy, just use the from equations that we have derived before. Okay. So it's just plain plugging in your values if you after you have known how to derive the equation, where does it come from and why is it in this particular form. And this one is your effective density of seats, which normally is going to be given during your examination as a constant. Okay, as assignment for your Webex conference, yeah, so please answer this question. I will open it shortly. Yeah, I give you 2 weeks to do this one. So this is as your bonus marks to help in your continuous exam. Okay, bonus, but I will only give you 2 weeks to answer this one, and you just upload it at the our e-portal. Okay. All right. Is there any question? Okay. Is there any question, anyone? Is there any question? Because time is up. So for the okay, please, yeah, upload your assignment, Webex assignment within 2 weeks so that you can get extra bonus marks that is going to be added to your continuous exam. Okay, since there's no question from anyone, okay, please, Nizama, please do your assignment. It will help you to increase your coursework marks. Begitu juga Ifa, Khairul, Ifa, Khairi, dan juga Syaril. Okay, and Nizam too. Okay, thank you for being here with me. I hope you will come also for our next Webex conference. Okay, thank you everyone. Okay, goodbye.